Hello, my name is Cecily Holland, and this is my assignment 3 recording for model analysis and simulation. Here you can see my code. I apply 2 different reinforcement learning environments, Gridworlds and Quentin's World, which are both images of grids. One is a 4x10, one is a 10x10. The Gridworld is a grid with a high penalty cliff along the bottom, and the Quentin's World is a grid with walls and traps that the agent must learn to avoid. So each environment is trained using basic Q learning algorithm and visualized with state action value plots, arrows showing best actions per state, and reward progression along episodes. A final grid showing the agent's optimal path from start to goal. The environments and plots are handled separately to showcase the distinct learning challenges and policies. So here you can see some of my imports. This is the environment that this file was provided, so that loaded that in. Here's the plot file that's loaded in, and then here is the Q learning and train function that I built. So you can see the structure here, and then running the Q learning and optimum path along with the grid plot show, and then here you're calling everything appropriately. This is the result for the Gridworld. So you can see here the agent starts at the left, the bottom left, and must reach the bottom right goal without falling into the cliff. The cliff region gives a heavy penalty of -100, so the agent must learn to avoid it by navigating carefully across the grid. After training with 500 episodes and using epsilon greedy Q learning, the agent successfully learned a safe policy. We can see in the quiver plot that the learned optimal actions consistently guide the agent along the second to last row, skirting the cliff while making efficient progress towards the goal. The optimal path extracted from the Q table is here. You can see it's very small. And this shows that the agent moves up at the start, travels right safely across the board, and finally drops back down into the goal state. So that's all for the Gridworld optimal path. And then moving on to the Quentin's World, you're calling all of the same functions. You're just inputting a different grid essentially, but it does the same thing, and the agent's trained on it accordingly. So you can see here with that 10x10 grid for this one, with walls and trap zones, creating a more complex navigational challenge. The agent starts at a state of 54 and must reach state 99. Several red zones penalize the agent, and there is also a shortcut mechanic that's built into the environment. After training, the agent found local optimal policy that loops around a narrow section involving the shortcut. In this run, the agent's optimal path was 55 or 54, 55, 65, 64, and then 65 again. So you can see that little loop. This indicates it's bouncing in a local loop, possibly exploiting the shortcut or avoiding nearby penalties. This kind of behavior can sometimes emerge when the agent finds a safe but non-progressive reward area and gets stuck due to the current reward configuration. So there's the visualizations for both. You can see this one was much more efficient, but for both environments, we visualized using the Q values for all state action pairs, a heat map of the maximum Q values per state, a quiver plot of the learned best actions, and then a grid-based path visualization showing the order of steps from start to goal. These tools help us not only to verify the learning occurred, but also to interpret the quality of the policy learned by the agent. Overall, this assignment helped reinforce how Q learning behaves in both structured and hazardous grid-based environments. The Gridworld results reflect a clear, converged policy, while Quentin's World showcased the influence of local traps and shortcuts on exploration and policy development. Thank you.